Okay, good morning, everyone. Welcome to the Carta Explore room. We have a number of people online this morning. It's great to see. And we have a special guest, Andrew Schwartz from the U.S. Army Corps of Engineers, who has done a number of assessment studies on the use of SLAM technology. And we're going to let Andy go ahead and take the stage. But before we do that this morning, I would just ask that in order to improve the audio quality, if everyone could please turn off their microphone. And with that, away, Andy.
Thank you very much. Thank you for inviting me to speak with you guys this morning. As you can see from the title of my talk that I have up, is going to be talking about, as Kathy explained, a couple of assessment projects that I performed with my office to look into SLAM technology because we have had in my industry, let me back up. I'm a geophysicist with the Army Corps of Engineers. I work primarily in the ordnance cleanup, environmental cleanup industry. And one of the capability gaps that we have had since I started doing this many, many years ago is the ability to accurately locate where we take measurements in GPS denied areas. So it's like in forests, as you see on the screen here. A little over 2 years ago, I started looking into the viability of SLAM technology to fill that capability gap. So, what I have, quick outline of what I'll be talking about for the next little while. We did two efforts. The first was literally a learning experience for me and my colleagues, as well as assessing the viability of the technology as a whole in terms of accuracy and precision of recording of where we walk collecting geophysical measurements. And then with the success of that, we went on to marry a SLAM system with a geophysical sensor and did a series of demonstrations, which I'll talk about towards the end. So I have a couple of slides to talk about the first assessment we did. We did a number of I guess, tests, you might call them. I'm showing here one of the several we did to give you an idea of the setup that we did. It was a very simple setup where we literally put a high precision GPS sensor right on top of in this case, the Stencil 2 SLAM unit that we used, and we stringed all the data into separate computers so that we could have completely separate and independent data streams to compare against. What you're seeing on the right-hand figure is, hopefully it's coming through on your side. You can see the track plot. I believe in in the SLAM community, you use the word trajectory. In the geophysical community, we use the word track plot. I'll use trajectory if I can remember to for the rest of this morning. So you're seeing the trajectory of both the SLAM and the GPS shown. And I even, in the blow up and the little blow up figure towards the bottom, you can see that the red plot is right on top of the black track plot. And this is about 60 minutes worth of walking back and forth. We call it mowing the lawn when our system is doing metal detecting. The purpose is to detect pieces of metal under every square meter that we're able to search. So we mimicked that kind of pattern here. The results were extremely encouraging, as you can see in this table here, that when we were done, we had a huge number of individual points. So the SLAM system was recording at 5 hertz. I believe our GPS system was also recording at 5 hertz. I used some geophysical software to do comparisons of nearest neighbor points, and you can see the statistics in this table here. The average polar distance and the standard deviations on the far right column are the numbers that led me to conclude that this is certainly was at that time. This is back in the July of 2019 timeframe. Certainly a viable solution for for using this as a navigation and positioning system for doing work in the woods. And that is what we did. So in early of this, or January or so of this year, we set about putting together a platform, as shown in the upper left corner, that could carry any reasonably sized metal detector. And what you're seeing in this picture is what we call an EM61. It's manufactured by a company in Canada called Geonyx. It has been the workhorse for UXO metal detection for probably about 20 years now, if not a little more. And the backpack is the electronics unit that drives the orange coil that you see. The name of the game for us in the UXO detection world is getting the metal detector close to the ground and very accurately recording where it takes measurements. And that accuracy is needed for a number of reasons, most of which deal around cost of doing business. Because sometimes the things that we're looking for are very small, and being able to pinpoint where they are to send a UXO technician out to go dig them, the more accurate we are in doing that, the less time they spend digging up fragments in a search radius hunting for the UXO that might be present. On the table to the right, you can see some specifications of the form factor that we have that we used. And when we take this system, so really quick, the looking back at the options that we have. So this is a picture of where we did work at a site up in a UXO site in Tennessee. You can see the woods, the forest in back of the metal detector. Getting accurate positions in that scenario is very difficult. The only solutions that we have that with the accuracies in the centimeter range that are available to us are have been a robotic total station, and the robotic total station is a very time-consuming system to use in the woods. So what we did for our demonstration was this area that you're seeing in the background was mapped using this exact same metal detector and a robotic total station by a contractor to the Army Corps as part of a cleanup at that site. We took our system, the one you just saw in the previous slide, and collected data in exactly the same location using the same metal detector, but using the SLAM technology for the positioning. So what I'm showing here on the left, as you can see in the title, is the trajectory of the RTS position data, and on the right is the SLAM position, the trajectories. As you can see here, it literally is taking keeping track of where you mow the lawn, except we're mowing it with a metal detector, not a grass cutter. And as you can see here, we do this very tightly spaced lanes. So these lanes are about 50 centimeters apart. That's the level of effort that's needed to find the kinds of small ordnance that might be present throughout the site. With that, the information, we're able to, when the metal detector is working properly and we have accurate location, we're able to make geophysical maps that look like these. The so the three demonstrations that we did were, first was to compare the data that we collected that was positioned with the SLAM system against the contractor's data set that was acquired with the RTS. And I have some statistics coming up on that. And the other two demonstrations I'll get into a little bit more. One was to take this technology onto a steep slope, which historically has been used or cleared using people with handheld metal detectors, because accurately positioning on a steep slope adds a level of complexity that has been difficult to overcome. And then lastly, we'll look at some ideas we had for looking under trees, because we are also responsible. Well, basically, we are normally responsible, the Army Corps, for cleaning up the land regardless of obstructions. And so we have to have a way of searching under obstructions, which we'll get at the very end. To a geophysicist's eye, these two maps are indistinguishable. A couple of things I'll point out in case you get some folks asking the questions on the scales. Our metal detector was deployed much closer to the ground, so we had much higher signal to noise ratio. I have adjusted the color scales on these two plots so that visually they are easy to compare with your eye. But the scales are different, and that is a key thing to the geophysical community that is something that I often get questions about. So on the next slide, oh yeah, so uh, probably the most important point for us from the environmental restoration program community is that the production rates that I was able to achieve. So on the robotic total station position data, the on average, and they cleared about a quarter to a half of an acre, not clear, they mapped a quarter to a half of an acre per day, which is a very slow production rate. And the reason for that is that multiple setups of the robotic total station are necessary because of the number of trees that are present. The robotic total station, in order to work, has to maintain line of sight between the total station and the prism on top of the metal detector. With the SLAM system, I didn't have that necessity. In fact, having the trees present is one of the things that helps keep the system or makes the system more accurate, is the way I understand it. So I was able to navigate unhindered by having to stop and set up, and was able to map the entire area in about 70 to 75 minutes for this one little, basically quarter acre plot. Uh, that is one of the key things that has us very interested, the Army Corps very interested in this technology, is the improved production productivity. Improved productivity is great, but it also has to meet our quality standards in terms of being able to tell us where pieces of metal are detected. And as you can see in the number of analyses that we performed here, we looked at one of the things that we do is we plant pieces of metal, so we call them seeds, throughout an area that we map. We know exactly where they are, and when a contractor comes back and detects one and tells us this is where it was located, our metric for those is usually 40 centimeters. They have to be able to tell us within 40 centimeters where we buried it from their detection map, as shown here. And as you can see with the SLAM system, we certainly achieved that very easily. The other things that we did was we compared the locations of anomalies that they detected to the same anomalies that were visible here. The figure to the left, the white circles, or white polygons I should call them, are the outlines of the anomalies that were detected in the robotic total station position data from the previous slide, overlaying onto the detection map that was acquired using the SLAM system. For the to a geophysicist's eye such as mine, these anomaly shapes and locations are essentially indistinguishable, which means that the technology worked as described, and we were able to do this analysis that we showed. The last thing that's often a very complicated problem is what I call beating down the noise. There's electronic noise and noise just from bouncing a metal detector through the woods that often presents a problem in terms of detecting small or deeply buried UXO. So the last thing we did was we compared the noise characteristics from the two data sets because they were we used the same metal detector. We're able to do this analysis, and that bottom table shows that quantitatively the noise are indistinguishable between the positioning systems. So basically, everything was a resounding success for us in this demonstration for comparing this data set to that collected with an RTS. So that's checkbox number one. The next thing that we did was took the system to a very steep slope. And here, let me start this video. I'm going to say right off the bat that this video was captured with a GoPro, which, because of the lens it uses, does not do justice to that hill. That hill is about a 45 to 50% grade, and it takes a lot of effort to trudge that thing up and down the hill. What you're seeing is what I call the start-stop method of acquiring data, and it's something we developed in my office, or came up with in my office about 15 years ago. And it literally is, we put the metal detector down and it's recording at 10 hertz. Then in post-processing, we take the data, we stack it and average it out so that we get a high signal noise ratio. The reason we did this on the steep slope was it was our first attempt at doing this. No one's ever done this before, to my knowledge. So this is the method we went with. The idea, the concept was we would um, use the roll pitch yaw information that is provided from the SLAM system to project from its measurement point, which is the center of the LiDAR, down through to the center of the metal detector to give us the centimeter level accuracy. And you can see here, this is the formula that we use, the rotation matrix transformation formula that we use. By holding the position of the SLAM unit as the point of reference, it becomes a simple addition or subtraction process that to apply to the calculated, or sorry, to the measurement to locate where the measurement as a metal detector measurement was taken in this formula. That too was very successful because, as you can see here, we were able to accurately position the data on that slope. What I'm showing on the right-hand side of the screen is the trajectory with where we went up and down the hill. You can sort of make it out. There are little black X's along the trajectory. Those black X's are the static locations where the measurements were taken. Those are the data that were used to make this plot. One of the things that I am very interested to look into, that I ran out of funding and ran out of time to do that, is to actually compare this to the data that was collected while we were moving it between stations. I believe that the system is sufficiently accurate with high enough update rates that we would be able to reproduce this map with a lower signal to noise ratio because we're not static, but to be able to reproduce it, and that would increase the productivity. The productivity on the slope for us was about the same as the productivity on the slope when it's searched for a UXO with a team of UXO technicians using handheld metal detectors, and we were about a half to an acre a day on this slope. So that was very useful for us. Oh, the last thing also for on the geophysics community, something that we don't always get is a digital elevation model, which you can see in that figure to the left. We're able to drape the geophysical data on top of that DEM, which comes out of the SLAM system. So it helps convey the information that way as well, which is very useful for our geophysicists in interpreting the data as where UXO may be located. The last thing we did was an idea that I come up with while doing this demonstration was we could just literally tilt the metal detector up against the trunk of a tree and project down how deep something might be detected if it were there. We have what's called forward modeling that allows us to predict how deep something can be detected, how deep a UXO can be detected beneath the coil. Again, using that rotation matrix formula, we can project how deep how deep something might be detected if it were there. And we did this over a series of about 8 trees. There's a lot of information on this slide. This is a brand new thing for us. But what I'm showing is a method that we might start employing to demonstrate to our landowners and to our regulators, EPA and state regulators who are concerned about the health and safety of the people in their area, that we can indeed search for UXO under tree trunks and doing it this way. So the red, blue, and green are the projected trajectories of where locations were searched underneath the tree trunks for different sized ordnance items. ISO in our lingo stands for industry standard object. And then what you're seeing on the far left is the modeled detection capability as a function of distance underneath the sensor. We can use that information with that rotation matrix and show where things would have been detected had they been there. All right, so that's what we did. In summary, we showed that the SLAM technology is very viable for the what used to, what I'm going to start saying used to be a capabilities gap in the GPS or GNSS denied areas. We were able to achieve very high production rates, and overall it improves with the addition of the roll pitch yaw information that comes in the data stream from the SLAM system. We're able to extract more information and get better accuracies than we have in the past. So our path forward, at least in my office at the Army Corps of Engineers, is to simplify the integration process for the I didn't go into how I did all of this. I suppose I should mention quickly the trick to my success was using a common timestamp where I used a little handheld GPS and a Y splitter cable to feed the GPS timestamp to both the SLAM system and my metal detector system so I could marry them up in post processing. There's a little bit to that that I don't have time to go into here, but it's all described in my report, which is shown here. And so with that, I'll acknowledge the folks who helped make all this possible, are listed here on the left. And the two reports that we have written, the first one is the assessment report, which I described at the very start, and then the demonstration report, which explains in much greater detail all of the demonstration work that was done, the processing and the analysis uh, that was used to produce the images in the previous slides. And with that, thank you for having me.
Thank you so much. It's a lot of information in a short period of time, and as you
That it
said,
is.
there is a full report. But if you have a couple of minutes, and if anyone in the audience has any questions, now would be a great time to ask them of Andy.
Hi, Andy. This is Kevin Dowling. I'm curious, you had mentioned the difficulty of doing the geolocation under the trees, under the canopy. What did you end up doing for that purpose to, within the SLAM system and all relative, you had good information, it looks like, from all of your charts, but how did you geolocate that? Um,
We pay a lot of money to land surveyors to put control throughout the project area. At that particular site, that contractor had put control in every 100 feet. Uh,
okay,
and one of the neat things that I was able to use from the SLAM output was I could see the lath on the control points that the surveyor had put in. So I was able to use those coordinates in the local SLAM coordinate system to rubber sheet the data very quickly and efficiently to real world coordinates for those monuments that they put in the ground. In fact, that's one of the key things for all the work we do, whether it's RTS, SLAM, or even less accurate positioning methods. But that's how we do it.
okay, great, thank you.
Thanks, Andy. I appreciate it. That's kind of what I was going to ask. Are you all using target-based systems at all to try to capture those in the scan? Or have
So
you guys used targets at all?
No, so this was a tremendous learning experience for me. As I mentioned at the very start, that very first effort was supposed to be just a learning experience. It turned out that your system is so simple for me to understand how to use. Um, you guys let me use it without the training, and I was able to do that as the assessment comparison to GPS rather than just take the time I had originally scheduled just to learn how to use it. Um, at that time, Dave had mentioned to me to put targets out, and I had forgotten to do that. My experience in doing this kind of marrying or fusing positioning data to geophysical data dates back a number of decades now. And I usually rely on the accuracy of the positioning system independent of the geophysical system, and I use common timestamps to marry them after both data sets look good or are pass all the quality control checks that they need to pass. The ability of having the point cloud is new to me. So I was learning on the fly and was able to use the lath when I could see them to do just that. And in fact, in the final, I think in both reports, he even mentions, at least certainly in the last report, as a lesson learned, is to put monuments or features in your point cloud that you can then use to extract coordinates from in both real world coordinates and local SLAM coordinates to do what I call rubber sheeting process to make that more simple.
Excellent. Yeah, very cool. Very cool.
Any other questions? Well, if there are, either A, get a hold of me, or B, read the report. There's
Andy,
a
I
lot of
have
info
one
there.
more question,
Shoot.
and that is, what's next? What's your next challenge or project to take these learnings and demonstrations and put them into real world use?
That's an excellent question. So there's a couple of facets to that. The first is on the technical aspect, this simplifying the merging or the merging process. And I know that you guys have been working with others to make that happen. I have been talking to folks in our industry as well, alerting them to the ability now to get accurate positioning under the tree or in the forest. So the first thing is for me is to get my folks in the Army Corps educated about this, and that was what you saw in that one of that the second to last slide. I do plan on hosting a series of training events for our folks to teach them how to do what I did, so that they can see how it works and get a feel for how it works. And that leads into the when I say when it works. So I'm sort of skipping over one of the parts, which is I think that the method I used can be used with any metal detector as long as I can stream a common timestamp into both systems at the same time, which most geophysical sensors have that if not all today have that capability. So that overcomes the major hurdle of marrying a SLAM unit or a GPS unit or an RTS unit with some geophysical sensor. Because very often you have to have a common language or a common series of information, positioning information, to get the two together, to get them to work together. The problem that I see here is that the roll pitch yaw information that I use to a great benefit is not a common part of that data stream that normally flows from a positioning system to a metal detector. So that's why I'm seeing the need still, at least in the short term, to have to process the two data sets independently. If the geophysical community picks up on this, or the instrument manufacturers pick up on this and have a way to take that the roll pitch yaw in as well as the XY or XY and elevation data, then that need will go away. But for the short term, that's one of the reasons that I see us pursuing this way. The second thing rolls into making it familiar to our contractor community, the folks who actually we pay to do the work for us. Is a lot of interest, but not a lot of experience yet. And I certainly, well, as Dave can attest from the several phone calls I frantically made to you guys while I was doing my demo, there's a lot of places where things can go wrong. And if you don't know where to look where they can go wrong, you can spend a lot of time trying to figure them out and maybe not figure them out. So our contractors very commonly are on a very fixed budget, very strict time schedule. So we have to have a system that they're familiar with and that they can use efficiently and expediently. So that will be the next part will be for us to generate the requirement to let them know that the DoD now recognizes production rates in forested areas can be in the 1 to 1.5 acres a day as opposed to the quarter to 1/2 an acre a day. So that will be that's the next challenge that my office will be working on as well, is getting that transition to happen.
If we can help with the communication to either the manufacturers and contractors, and I know Dave's in touch with a couple, we would be happy to do that as well.
Fantastic. I'll keep that in mind.
We like the idea of helping set the standard.
Yep.
Yes.
All right.
Excellent.
Any other questions, anyone? Okay. Well, Andy, thank you so much for your time today, for sharing all of the findings. We did record this presentation, and we will be making it available on our Intergeo stand and likely on our website as well.
Fantastic. Well, it was my pleasure.
Great.
Thank you for having me.
All right.
Thanks, Andy.
Thank you,
You're
everyone.
welcome. Bye-bye.
Bye-bye.